Alright, so welcome to Unit 4. In this video, we'll be talking about single degree of freedom responses to arbitrary loading. Now, if we recall back to the previous unit, that unit focused primarily on sinusoidal inputs or harmonic loading, and the analysis was mainly restricted to the frequency domain and steady state, right? In this unit, we're going to be changing the perspective a little bit. We're going to be generalizing to arbitrary types of loads where we need to know exactly the loading profile, and our analysis will be mainly focused in the time domain, right? So we'll be able to look at things like transients, and this is particularly important for more unpredictable loads such as earthquakes. Alright, so this unit is primarily broken up into two main sections, impulse loads and step and ramp loads, and you can see the associated textbook sections here. In this video, we'll be dealing with impulse loads, and in the following video, we will move into step and ramp loads and combination of these loads. So let's talk about impulses. So an impulse in general is defined as a force which acts over a very short period of time. So here we have a force P which begins to act at a time t and is constant over a time period delta t. For this to be considered a unit impulse, the area under the force curve needs to be equal to 1. And for that to happen, we need a height of 1 over delta t. Now this is a nice conceptual picture of what the unit impulse looks like. On the right side, we have a more theoretical picture, a little more analytical version of this function, which is useful for deriving a lot of the properties and equations that we will be deriving in this video. The Dirac delta function is defined as this unit impulse as that interval delta t approaches 0. So as delta t approaches 0, that impulse gets squeezed, and so we end up denoting that as essentially instantaneous pulse at time tau. Now this pulse is, of course, approaching infinity as delta t approaches 0. Keep in mind that the function is defined everywhere else as well, where it takes on the value of 0. Now, the basic definition of the Dirac delta is this delta function of x, and it can be loosely thought of as a function which equals positive infinity when x is equal to 0 and 0 for every other value. All right? Now keep in mind that this is a loose definition, right? The function doesn't actually reach infinity because it's only defined in terms of a limit. In a more general sense, we can define the delta function using this shift delta tau, right, which we introduce here, which will slightly change the definition to positive infinity when t is equal to tau and 0 when t is not equal to tau, which is closer to the illustration that we have up here. Okay, again, keep in mind this is a loose definition. The strict definition is that delta is the limit of the unit impulse as delta is approaching 0. And the only property that we really know about the Dirac delta function is that the area is in fact equal to 1. Now let's apply the Dirac delta function to derive a very useful property of dynamic systems, which is the impulse response. Okay, so let's start by assuming that we have, again, our typical mass spring damper system, and we're going to be applying a load that is an impulse load. And we're going to express that impulse in terms of the Dirac delta. So we're going to take the Dirac delta, shift it by some time tau, right? So we can account for an impulse at any point in time. And we're going to scale it by this constant I, which is going to represent the magnitude of that impulse, right? So again, we're just trying to generalize so we deal with more than just a unit impulse. We're going to assume that the initial condition of this mass is 0, so it's just stationary. And if we apply Newton's second law, right, again, I'm going back to the general definition that it's defined as the rate of change of momentum, so m times velocity. And that rate of change of momentum should be equal to the force applied, which in this case is exactly what we defined, I times delta t minus tau. Now if we invoke the impulse momentum relationship here, we can actually integrate both sides of this equation to make it a little bit easier to process. So we're going to integrate the left side from a time 1 to time 2, and I'm going to define this time 1 and time 2 as the time right before and right after the impulse. Okay, so let's say we have our load P and time, and then we have at time tau unit impulse scaled by I. All right, and I'm going to define time t1 as the time right before this, almost instantaneously before, and the time instantaneously after the impulse is t2. So we integrate both sides. On the left side, it's pretty easy. The integral cancels out the differentiation, and we just get the rate of change in momentum from time t2 to t1. I'm sorry, not the rate of change, just the change in momentum from time t1 to t2. And that is equal simply to the velocity at time 1 subtracted from the velocity at time 2. And on the right side, I is constant. It's a constant scalar fractal, so that goes out of the integral. And because of that useful property of the Dirac delta, that the integral is equal to 1, this integral simply just goes to 1, and so we're left with I on the right side, right? So this is what we mean by the impulse momentum relationship. We have the change in momentum is equal to essentially the area under the force curve. All right, so because T1 and T2 are immediately before and after, we can say that right immediately before this actually should be denoted as the velocity in all cases. So the velocity right before at time t1 is equal to 0, right? The mass is not moving. And then we're just going to generalize the velocity at time t2 as simply the velocity at time tau. Okay, we're going to assume that's basically right on it, right? We want to see what the new velocity is right after the impulse has occurred. And if we plug that in, we get a pretty simple relationship, which is m times u of tau is equal to 1. And we can simplify that to u at time tau is equal to 1 over m. Okay? Okay, so this is actually a pretty fundamental and important result, because it means that we can express essentially the impulse as an equivalent free vibration response, right? We saw just now that the initial velocity essentially right at time tau is I over m, so it can be defined in terms of the impulse. So if we look at the equation of motion, we can say a system which is loaded with an impulse with zero initial conditions can be expressed as a unloaded system with an initial velocity at time tau equal to 1 over m. In this case, I'm just using I equal to 1. And this leads us to the definition of what we call the impulse response. Or IR. Sometimes it's also called the unit impulse response. Okay, and this is this value h. Okay, and h is simply defined as the u which solves that equation of motion that you see here, right? And if we look back through our free vibration unit 2, you will see that that is simply this function right here. Okay, the only difference is that we've shifted the two time terms by a quantity quantity minus tau. Okay? And keep in mind that this equation is only defined for time greater than tau. H will be defined as 0 for time less than tau. All right, so that's very important. So let's look at what that looks like graphically. So if we've got a force P, which is a unit impulse that occurs at time tau, don't worry so much about the quantity epsilon here. Let's just think about this as a instantaneous pulse delta, and I should shift that delta over to tau to be precise. So this is an instantaneous pulse at tau. Then the impulse response will be equal to what you see here. It will be 0 for time before tau, and at time tau it will look like a free vibration response with an initial velocity, right, an initial slope of 1 over m, and depending on whether it's undamped or damp, it will either continue to oscillate or decay. Now, why is this important? Well, the unit impulse is important because if we think about this in terms of time, we can always describe any arbitrary force as a superposition of impulses. And this being a linear system, we can always break it up into individual impulse responses and then superimpose the responses back together again. And that's exactly what we're going to do. So let's consider now an arbitrary function, p of t, as a set of shifted impulse loads, essentially a sum, a superposition of shifted impulse loads, as you see here. So each segment of this function, right, let's take an arbitrary segment at tau, is going to be described as essentially an impulse load, right? And so we're going to treat that as just a rectangular load there, right? So the area of this impulse is going to be p of tau right? The value of the force at that moment in time times delta tau. I should say d tau to be precise, d tau. Okay, which is the width of that impulse. Now, as you can imagine, eventually that d tau is going to approach to 0 and we're going to get a Dirac delta. But just for visual purposes, we're going to split it discretely here. So, right, if d tau is sufficiently small, then the response to that segment of the force, which spans from p tau to p tau plus d tau, you see here, then it's simply going to be the unit impulse response times the magnitude of that load. So times the area, right? So it's going to be p tau d tau, the area, right? This is the I, so to speak, the magnitude of that impulse times the unit impulse response, which is t minus tau. Okay, so we're simply scaling the unit impulse response based on the magnitude of the force at that particular instance. And then the total response will simply be sum of all the shifted and scaled impulse responses, right, which can be expressed as the sum of all the impulse responses at every tau from 0 to infinity, right? And each of those responses, of course, will be a function of time. So that is what this looks like graphically, right? So we have an arbitrary input function, p, which gets split into little segments, and for each segment, we take the unit impulse response and scale it by the magnitude of that segment. Okay? So we take the value of p here and scale essentially the slope of that free vibration here. Then we shift over by just a little bit to get the force at this point. We do the same. At an arbitrary time tau, we're going to shift over by tau, as you can see. Here, again, scale it, right? So you can see that as the force gets bigger, as is the case here, the slope gets larger in the impulse response. Okay, and then we simply just take all these impulse responses, sum them together to get the total response. And unsurprisingly, the total response somewhat follows the shape of the loading pattern, right? As you can see, but it oscillates around that pattern. And without going too much into the theory here, we'll simply go straight to the result and say that as that d tau, right, as we go away, move away from the discrete type of thinking and squeeze that d tau to 0, right, this should be 0 instead of infinity, that sum converges to a pretty simple integral actually, which is the integral from 0 to t of the loading function, p of tau, times the impulse response function shifted by tau. And this is called Duhamel's integral, and can also be thought about convolution as a convolutional integral, which is how this general type of function is defined. If we are going to make this explicit, we would say that the general arbitrary loading response u of t to some load p of t is going to look like 1 over m omega d times 0 to t, the integral times p times tau, right? So all I did was took the definition of H, which we got up here, rearranged it just a little bit, so I drew the 1 over omega d to the outside, and that is basically it. So that is your damped response. All right. The undamped, I'll leave it for you to find. Simply you can replace zeta equal to 1. Sorry, zeta equal to 0. But the important and fundamental thing to realize here is the fact that essentially this response is the most general type of response function that you can achieve, right? Because it will give you the response to any type of function, right? And so there is no more general response function than this. So if you have this, technically you can derive the response to any type of loading. The caveat, of course, is that evaluating that integral is not always so easy, right? So it's not necessarily the most practical form. But fundamentally speaking, the impulse response function gives us all the information we need about the dynamic response, right? Because essentially we can simulate the response to any type of function, any type of loading function using this integral, which at the basis has this h, this impulse response function, okay? So with that, we'll finish up this first video, and in the next video we'll be talking about arbitrary loading for different types of inputs such as ramp loads and step loads.